and welcome back to today's episode of the Funtastic Academy. Today we're going to be covering ALUs or Arithmetic Logic Units. ALUs are the core processors inside the system you're watching this on right now. They do all the calculations, addition, subtraction and comparisons to make your computer run. Now, before we continue, I'd like to say that this is the 4-year anniversary of Funtastic Academy on 28th of December 2024. Thank you for all your support in helping us produce these monthly videos through the years. Now, let's get the quiz question. What's the quiz question? From last episode, it was which company was the first to commercialize and popularize the hard disk drive? The answer is Intel. Intel was the first popular company to sell hard disk drives. So now that we've got that out of the way, let's explore how ALUs work by diving in. Thanks for that, camera Ayush. Now we're back in the computer, specifically in Circuitverse. Circuitverse being the top-notch circuit simulator that I use in all my videos. You can see I've already done some setup, creating a basic full adder and 4-bit adder using the ripple carry method. Now ripple carry isn't exactly the fastest. I've shown off previously the carry look-ahead adder method that works much more efficiently and which virtually all computers nowadays use, but for the purpose of our simulation, it won't really matter. What we're focusing on today is how to implement subtraction and how to wire control signals into an ALU. For the example of the latter part, we can just see the ALU that Circuitverse has here. Because, of course, Circuitverse is a quite high quality simulator and they have a bunch of other circuits other than the simple gates. For example, the ALU. Now, most ALUs, such as this one, will have 5 main categories of input/output, which we are going to emulate. First, A and B, the two inputs which we want to add or subtract or do anything really. Then, the control signal. This control determines what we want to do with them. Add, subtract, compare, whatever. Now, in our basic ALU, we are only going to have two possible operations, addition or subtraction. So this can essentially be treated as just a subtract bit, a single bit. In the Circuitverse ALU, it's quite a bit fancier, so it has a 3-bit control line for 8 possible operations, including bitwise adds and ors and comparisons. Obviously, we have to output the output of whatever operation we're doing. And finally, control flags. These flags give us more information on the output so that if we want a specific detail, we can use them. For example, has there been a carry in this output or is the output equal to 0? These flags can be used in high advanced computer architectures to execute jump instructions, but we won't worry about that now. So, let's start with a simple question. How to make a subtracting circuit? Luckily, we already know how to do this. A few episodes ago, I introduced the 2's complement method for subtracting numbers in binary. The idea is that 2's complement can turn a positive number into its negative equivalent and vice versa. So when you want to take 6 minus 4, you can take 4, turn it into minus 4 with 2 complement and do addition, which we know how to do, to calculate 6 plus minus 4. But how do we turn 4 into minus 4? With a negation circuit. I'll just build one right now, call it a 4-bit negator. And 2's complement is luckily extremely simple. All we have to do to negate a number is take all its bits and invert them and add a little extra 1 onto the end. So we can just do a little cut here while I set up all the inputs required for a negator circuit. Alright, so I've set these up. We have the 4 inputs into our negator and we've inverted all of them using the NOT gate. So we have the inversions. All we've got to do now is add 1 to them. We can insert the 4-bit adder sub-circuit that I already had ready and then wire them in. So we wire them all up to the A's in this circuit. A1, A2, A3, and A4. Now to add 1 to this, we could just input a constant value of B1 of 1, B2, B3, and B4 zeros. But the simpler and smarter way to do it is just put a 1 at the carry in line. I'll use the constant value feature of Circuitverse and put it at the carry in. It essentially acts as another version of the B gates, but it can only hold a 0 or 1. Exactly what we need. So now we can just pull out our output. And we are currently calculating -0 or the inverse of 0, 0, 0, 0, which as you can expect is 0, 0, 0, 0. But if we want to calculate something else, such as -4 from that example, well, we can turn on in 3. What is the number we have here? 1's place, 2's place, 4's place. The 4's place is on, so we got a -4. The inverse of this is a 1 place, 2 place, 4's place, and 8 place. So 4 plus 8 or 12. 12 is -4 in this system. Now if we have 12 plus 4, what happens? 16. But since we only have 4 bits, 16 will loop back around again and equal to 0. It's like when you have those ticker tape wheels on a calendar and you have 999. If you advance them once, the wheels will all rotate and show 0, 0, 0. That's what's happening here. 12 plus 4 equals 0. And there we have it, our negator circuit. In summary, what did we learn today? Well, this is part 1 of a 2-part series, so we haven't finished building the ALU yet. But we finished working on what the inputs and the outputs of our ALU should be, as well as building the negator circuit. In the next video, we'll work further on completely wiring and setting up our ALU. In the meantime, a simple quiz question. Who was the first scientist to implement the use of binary 2's complement in the area of computing? Tell me the answer and I'll see you on the next episode of the Funtastic Academy. Bye!